Welcome to the lecture on zodiacal emission. This lecture is part of the Cosmological Component Separation course at the University of Oslo. This lecture will consist of three parts. In the first part, I will introduce the physical phenomenon that creates the zodiacal emission. In the second part, we will look at why and how zodiacal emission differs from the usual static foregrounds that we are used to think about. And in the third part, I will introduce how we typically model zodiacal emission. My name is Metin San, and I'm a PhD candidate at the University of Oslo. For my master thesis, I worked with zodiacal emission modeling in Command. We will start by learning about interplanetary dust, which is in many ways similar to thermal dust. Similar to how dust grains are scattered throughout the galaxy, we also observe a collection of grains locally within the solar system. The size of these grains range from 1 to 500 micrometers, with most being in the 5 to 15 micrometer range. If you watch the thermal dust lecture, you may remember that galactic dust tends to be in the 0.01 to 0.2 micrometer range, making the interplanetary dust grains much larger than its galactic counterpart. The interplanetary dust is actually visible from Earth just before sunset or sunrise, at which it appears as a faint triangular glow known as the zodiacal light. The name zodiacal light was first used by the famous astronomer Cassini, who was the first to correctly describe the phenomenon as being sunlight reflected from dust grains. The optical light reflected from the dust in itself is not a problem for CMB cosmology. However, these dust grains are also heated by the sun, which causes them to radiate thermal emission at high microwave frequencies and in the infrared. We can see what the zodiacal emission looks like in galactic maps in these two figures, which show the observed emission from the IRIS experiment at the top and the Derby at the bottom. The first thing we notice is the shape of the emission. Since interplanetary dust is a foreground local to our solar system, the emission is aligned along the ecliptic rather than the galactic plane, and hence this S shape. The zodiacal emission quickly becomes the dominant foreground on the sky at high microwave and infrared frequencies, as we can see in the 60 micrometer Derby map, which is at around 5000 gigahertz. So in the second part, we will look at why zodiacal emission differs from regular static foregrounds. When we model foregrounds, we typically assume that the emission from them are originating from the surface of a shell infinitely far away. This assumption holds because the observer is so far away from the source such that the observed emission is the same no matter where the observer is located in the solar system and when the observation was done, at least for any relevant timescales. Unfortunately, this assumption breaks down for zodiacal emission due to its close proximity to us, the observers. This figure illustrates two observations made from Earth at two different times throughout Earth's orbit. We can see that two parallel lines of sight observing a source infinitely far away will look through different columns of interplanetary dust at the two times. To illustrate what this difference would look like on maps, I have created two simulations of the observed zodiacal emission as seen from L2 3 months apart. We will come back to the specific appearance of the emission a bit later in the lecture. Just to show some real-world examples of this variation, I will briefly show the zodiacal emission in the Planck experiment. In these images taken from the Planck 2013 zodiacal emission paper, we can see that two frequency maps for the 857 GHz detectors, those in the top and the middle here, over two different surveys. These maps looks identical to the eye, but taking a difference map, as seen here in the bottom, reveals the S-shaped zodiacal emission. Hopefully this illustrates the difficulty of making a single zodiacal emission template that would describe the emission seen by any experiment in general. The observed emission will always be a function of the specific scanning strategy used by an experiment. That being said, if an experiment observes over very long times, and by that I mean where the Earth has had time to go around the Sun several times, then the averaged emission over the entire observation will become much more symmetrical around the ecliptic. And we can see an example of this in the simulated map here, where I have averaged a set of observations taken at equally spaced times over a year. Now, for the final part of this lecture, we will discuss how one can go about actually modeling zodiacal emission. And I will begin by introducing interplanetary dust models. There are two main components to zodiacal emission modeling. The first component is related to estimating how many dust particles an experiment looks through at any given time during observations. In other words, we need to compute the column density of interplanetary dust seen through the beam of an experiment at all times. For this purpose, we need an interplanetary dust model, which describes the three-dimensional dust distribution in the solar system. The currently most widely used interplanetary dust model is the Kelsall model, which was developed for the Derby instrument of the COBE satellite for the purpose of removing zodiacal emission in their data. The Kelsall model is a three-dimensional density model consisting of 5 zodiacal components, those being the diffuse cloud, 3 asteroid bands, and the circumsolar ring. The density of the components can be seen in these figures, which shows contours of the dust density of each component in a cross-section of the solar system perpendicular to the ecliptic. The circumsolar ring includes an enhancement known as the feature, or the trailing feature, which is often separated into its own component. The x-axis in these images are in AU. The model is defined in heliocentric coordinates, but each component is allowed to be slightly offset from the heliocentric center, in addition to having a tilt with respect to the ecliptic given by I, the inclination, and omega, the ascending node. This offsetted coordinate system is denoted by the primed coordinates. Every zodiacal component, with the exception of the Earth trailing feature, is assumed to be symmetric in a plane defined by the inclination and ascending node. And this makes it very easy to express their densities in the primed coordinates. R prime and C prime denotes the distance to some point in three-dimensional space and the height above or below the ecliptic plane at that point, respectively. The R prime and C prime coordinates is therefore all that is needed to get the density of a symmetric component. The first and largest zodiacal component is the diffuse cloud. This is a massive cloud of dust grains that encapsulates the solar system. Its density is given by this expression. The specific form of this equation is motivated by the Poynting-Robertson effect, which is a process where radiation from the sun causes orbiting dust grains to lose angular momentum, and this results in the grains eventually drifting in towards the sun. Note that the parameters that appear in this density expression that was not described in the previous slide are free parameters. There are over 40 free parameters that describe the geometry of the components in the Kelsall model. The next components are the asteroidal bands, which are believed to be the remains of asteroid collisions or comets falling apart. These appear in pairs around their symmetry planes, and it is possible to relate these bands to specific asteroid families that appear at similar ecliptic longitudes. 3 such bands were included in the Kelsall model. The final components are the circumsolar ring and the Earth trailing feature. Major bodies in the solar system will trap interplanetary dust grains in circumsolar resonant orbits. The Kelsall model therefore includes such a component around the Earth, where the effects of these trapped grains would be most relevant to an observer. But in practice, there should be a similar enhancement around most major planets. Furthermore, an enhancement in this resonant orbit is included in the region trailing the Earth, given by theta, the heliocentric longitude of the Earth. This is the so-called Earth trailing feature, and it's the only non-symmetrical component in the Kelsall model. Here we see what the ring and feature looks like from above, where the Earth has been plotted as a blue dot. And we can see that the feature enhances the region trailing the Earth. And here we see some simulations of what the density distribution of each component would look like on the Earth at a given day, specifically at the 6th of October 2021. These are very useful to look at since the emission will trace the density. The appearance of the circumsolar ring and the Earth trailing feature can look very weird at first eyesight. However, if we go back to the contour plots, we can see that this actually makes sense. So let's consider these two brightening regions in the circumsolar ring. If we look at this contour plot, we can see that when an observer looks in this direction along the ring and in this direction, they will see more dust in the line of sight, hence this brightening. We can also see that there's some brightening occurring perpendicular to the ecliptic, and this we can see if we look at the cross-section contours here, where when you look perpendicular to the ecliptic, you again will look through more dust. It should be noted that this is only the case for an observer located near the Earth, more specifically within these enhanced dust regions. For the final part, we will discuss how we can use this interplanetary dust model to estimate the zodiacal emission seen by any observer. Okay, so now we have a model for how the dust grains are distributed in the solar system. We should be able to compute the column density seen by an observer. But first, we need to consider the nature of the radiation emitted by these grains. A natural place to start is to assume that these grains would behave similarly to galactic dust and emit some form of blackbody radiation. It is also fair to assume that the radiation emitted by the various zodiacal components will slightly differ due to the different compositions. It is also fair to assume that the radiation emitted by the various zodiacal components will differ, since each component is associated with dust produced by some specific type of body. As an example, the asteroid bands are associated with very specific asteroids and will therefore depend on the composition of these. But in order to compute the blackbody emission, we need to know the temperature of the various dust grains, which is given by the interplanetary temperature. This is the temperature that the radiation of the Sun heats dust grains to, and it is assumed that it falls with distance from the Sun as 1/r to the power of some delta. T0 is the interplanetary temperature at 1 AU. Keep in mind that this interplanetary dust temperature is just an assumption, and it is unlikely that a single grain temperature exists for each distance r. In reality, this will likely depend on the composition and size of each grain. Combining the interplanetary dust model and the emission mechanism, we can now estimate the integrated emission as seen by an observer. So let us assume that an observer is looking along a line of sight to some faraway point on the sky. The contribution to the sky intensity seen along the line of sight will then be given by the product of the density of that component with the blackbody function integrated along the line of sight. Furthermore, to correct for the fact that dust grains aren't perfect blackbodies, it is common to scale the resulting integral with some emissivity factor. This factor is usually a free parameter, which we can fit. In practice, for any given experiment, the observed zodiacal emission will need to be estimated along with the time-ordered data to make sure that the correct line of sights are drawn. In Commander, what we currently do is that for each chunk of time-ordered data, we query the observer location, and then for each unique observed pixel in that chunk, we construct a line of sight and integrate the emission for each zodiacal component along that line of sight and sum it up. The integral is typically cut off somewhere around 5 to 6 AU due to small contributions from the dust outside of these regions. Despite the fact that Commander currently lacks the integration of a high-frequency dataset where we could detect any meaningful zodiacal emission, we have made some simulations based on the pointing and time-ordered coordinates of the Planck LFI data, which is currently integrated into the framework. In the following plots, we see simulations of what we think the zodiacal emission seen by the Planck HFI instrument would have been. Note that the relative emission of each component changes with frequency. This is the corrections made by the emissivity parameters, and it is a possible result of the varying composition of the dust grains in each zodiacal component. And that concludes the lecture on zodiacal emission. To summarize, the zodiacal emission is a dynamic foreground unlike regular galactic foregrounds. It is therefore impossible to make a universal template that will be able to correct for the zodiacal emission in every experiment. Instead, we need to produce zodiacal emission maps custom to each dataset. To produce such maps, we need a 3D interplanetary dust model that describes how the dust grains are distributed in the solar system, which we can then use to compute the observed intensity in the line of sights observed in the data. And finally, the simulations shown in this lecture was produced using Zodipy, which is an open source zodiacal emission simulation tool that I have developed in Python. If you found zodiacal emission interesting, feel free to download and try it out yourself.